Hello and welcome to this presentation on Ansys Workbench Mechanical. We're going to look at the problem of finding path results in problems that have cyclic symmetry. Occasionally questions come from customers when they try to do this without success, and I'm going to illustrate a simple model here. This model has 1/8 of a complete wheel. You can see the coordinate systems that are placed on the axis of what would be a complete wheel. There's the original global coordinate system, and we've created a cylindrical coordinate system in the same place in space. We've put a path into this model running through the thickness of this part, and we've put in a symmetry object, a cyclic region using the cylindrical coordinate system, and you can see low and high sector faces on the wheel. This will give us a model with cyclic symmetry behavior. Here's a mesh. We've set it to be rather fine, and we've asked for multi-zone meshing so that we happen to get a mesh that is mostly hex elements. It's a simple linear model. We've put in a rotational velocity around that z-axis in the cylindrical system, rotating at 3600 RPM, a common speed for an electric machine in North America. We've also put in a minimal amount of constraint on movements. We've taken one vertex. We've indicated that we don't want it to move in y, which is the cylindrical direction, or z, which is the axial direction, and we're expecting that other possibilities of movement will be eliminated by the cyclic symmetry that we've applied. So we have a model that's ready to solve. Solution is quick. We get a deformation that looks like this. Now in Workbench Mechanical, they've programmed it so that if you have a cyclic region, it will use computer graphics methods to show you the deflection of the entire model. Here's the complete wheel. Here's the stress pattern. And you can see symmetry in the stress pattern. So even though we have a geometry that consists of only one sector, you can see results over the entire model. The difficulty this introduces is that you can't get it to give you a path result. Let alone a linearized path result, you can't give it to give you any path result. And if you try to solve, you'll get a message that says, invalid scoping method. You can try to force an ordinary path result. Insert, for example, a deformation, total deformation, and you can do it for geometry or named selection, but it will not offer you a path even though one exists up here. So we seem to be stuck. If we go into the Ansys Customer Support Portal, we see that paths are not supported when cyclic symmetry tools have been employed. Here's an older approach to modeling cyclic symmetry that gives us the means of examining path results. It's the same geometry. We have constructed a path. We've put in a cylindrical coordinate system once again. We've meshed the model, and once again we've used a method in meshing called multi-zone in order to get mostly hex elements. But let's get into the meat of the matter. Same kind of analysis, same rotational velocity, a displacement constraint once again, and we've put in some APDL commands. Now let's go back up and look at that coordinate system. We've given it the coordinate system number 9999. That's just for convenience, and we use a large number, larger than any other coordinate system number that could exist in the model. We go down then, and we use a command available in Ansys called cpcyc. What this command is doing is coupling nodes in all directions, all degrees of freedom. There's the coordinate system reference, 999. It's no displacement at x, a 45-degree displacement in that cylindrical coordinate system. and we're asking that the nodal degrees of freedom be rotated by the angle. This command causes a search looking for pairs of nodes that are 45 degrees apart, and it couples them. It actually sets up coupling commands. If we go back and look at it, it is a 45-degree sector, so we want that 45-degree offset. And in the meshing controls, we've included what's called match control. And we're saying that for two chosen faces, low and high sector faces, in that global coordinate system, we want a matching mesh. So when I do produce the mesh, I get nodes offset in space. For the command to work, the faces have to have the same shape. Those faces can be curved. They don't have to be flat planes. They can be curved, and we can get cyclic symmetry working as long as the geometry of the two faces will match, and the match control takes effect, and we get matched up nodes so that the 45-degree offset can couple them. With that done, we can run the analysis. We can see the total deformation, but lacking the symmetry group in the outline, we no longer get the 8 sectors plotted in using computer graphics methods. But we have the same kind of a deflection, the same kinds of stresses, and you can go down and put in some APDL commands if you wish to. Here I've set the last solution, send plots to a PNG file, take a view, nodal solution plot, element solution plot. Here I plot the elements, showing the coupling symbols. I do it from 2 different angles in space. Let's go see the plots that come out in APDL style programming. There's the model. There it is without averaging. There's a view of the elements with the nodal coupling, and it's more easily seen directly from the front. You can see that the nodes have been coupled. Those nodes found 45 degrees apart, and if you see the direction these little triangles point, you can see that the nodes have been rotated 45 degrees, so that tangential movement here is coupled with tangential movement here with a 45-degree change in the direction in the cylindrical Y or tangential direction. So this is our workaround to put those APDL commands in to get coupling for cyclic symmetry with that 45-degree offset referring to the correct coordinate system, and seeing the same kinds of results that you can see when you do the more modern approach of symmetry objects. But what you can do now is get path results. So there's a path, results on the path, and they can be linearized. So here we have a linearized path result, giving us the objective that we were after. So there's your workaround. Thank you for joining me.